I'd like to take you through one example of calculating certain things about waves on a string. This is a question about a violin string. So it says that the wave on the string travels at 600 meters per second. If the string is 1.1 meters long, what is the fundamental frequency? Now, this term, fundamental frequency, is not something that we've previously discussed. So the fundamental frequency is the lowest kind of the longest wave that will be created in that string, the lowest frequency that can be created, right? So fundamental frequency is what we refer to as the first harmonic, right? So this will be the lowest frequency that's created, and as we create different frequencies in the string, they are multiples of this fundamental frequency, right? So when we're looking at the fundamental frequency and we're looking at a string, we know that the fundamental frequency is essentially the longest wave that can be created in here. And so that is the whole string just kind of vibrating over that equilibrium line. So this is what this will look like. This is our first harmonic, and this is the fundamental frequency. So in the problem, it tells us that this length L is 1.1 meters. And so from here, we should be able to actually calculate the frequency of this wave. So things that we know. The length of this is 1.1 meters, and there's half of a wave in this. So the length represents 1/2 of a wavelength. Right? And so this kind of goes back to what we looked at in the notes section about how to calculate the wavelength and determine how many waves are in here. Okay? And so this is essentially our first harmonic. And so we're going to put that 1 in here, right? So kind of your overall equation for this, your overall relationship is L is equal to N over 2 times the wavelength. And so you'll see that as I kind of work through this. So I have 1.1 meters is equal to half of a wavelength, which gives me one whole wavelength is 2.2 meters. Okay. So now using some of the given information, I can calculate the frequency of this wave. So this told us that the speed of the wave was 600 meters per second. So we're just going to use V equals F lambda. So 600 meters per second is equal to that frequency times the wavelength, which is 2.2 meters. And so if we divide 600 divided by 2.2, we get a fundamental frequency of 272.7 hertz. Right? You could do 2 decimal places like we normally do, 272.73 hertz. Okay? So this is my fundamental frequency. This is the lowest frequency that's created. Now, the next thing I'd like to do is look at the next wavelength that's allowed in this string. So if I look at my next frequency, right, the consecutive frequency that's created, instead of having 2 nodes and 1 antinode, we're going to have 3 nodes, right? So I'm just going to draw those first. So we're increasing the number of nodes by 1. And then I can draw my wave. So this is my second harmonic, and my length here is still 1.1 meters. Right? And so in this, you see that we now have, if we call this my second harmonic, right? So L is equal to my second harmonic, so N, so 2 over 2 times the wavelength. Well, 2 over 2 is just 1, so L is equal to the wavelength. And so my wavelength is equal to 1.1 meters, right? And you can see that here I just have one wave. So now if I calculate the frequency, my next frequency allowed, we're still going to use V equals F lambda. The speed is still 600 meters per second. We can find this frequency. So when I do this calculation, I get a frequency of 545.45 hertz. Okay, I'm going to go one more. So let's look at the third harmonic. Right, so I'm just going to shift over here. Right, I know the problem doesn't say to do this, but I just want to show you this relationship here. So third harmonic, instead of having 3 nodes, we're going to have 4. So 1, 2, 3, 4, and then I can draw my wave. Okay, so I have 4 nodes, and I have 1, 2, 3 antinodes. Right, just something to take note of there. Right, so that's what my wave looks like. The length is still 1.1 meters. Right, and so we're looking now at my third harmonic. So if I use that general relationship, right, L is equal to the number of the harmonic divided by 2 times the wavelength, that means that I have L equals 3 over 2 times the wavelength. Right, so that means I have 1.5 waves in here, which you can see. So when I plug this in, I get 1.1 meters equals 3 halves times the wavelength. So my wavelength now is getting smaller, so 0.73 meters. And then again, if I use V equals F lambda, I can find the frequency of that third harmonic. 0.73 meters. So my frequency here comes out to be somewhere around 821 hertz. Okay, and so what you should do here is look at the relationship between each of the frequencies that are created. Okay, so this is my fundamental frequency, and each consecutive frequency should be another fundamental on top of that. Right? So what you can imagine is this shape is a fundamental frequency. When I add another half of a wave, I'm adding another fundamental frequency. So I'm going to double this. And so 272 times 2, right, gives you 545. And then when you go to the third harmonic here, what you're going to do is add the fundamental frequency. So you're going to add 272 hertz to 545, and you get something close to 821, right? And so what I did, since we rounded, it won't be exact, but it's pretty darn close. So each consecutive harmonic, you're adding another fundamental frequency. Right? That will help you in some of the questions that you'll see that I'm going to have you try.